Obrigado, Luciano. So thank you all for being here. So let's start the PhD defense of Juan José Quiroz Omaña, who will be defending his PhD thesis. And after an exposition of 15 minutes, the thesis will be evaluated by a PhD committee composed of Abderrahman Kedar from the Laboratory of Informatics, Robotics, and Microelectronics of Montpellier, France, by Dr. Murilo Marques Marinho from Department of Mechanical Engineering of the University of Tokyo, Dr. Luciano Pimenta from the Department of Electronics Engineering of UFMG, and Dr. Vinicius Mariano Gonçalves from Department of Electrical Engineering, also from UFMG, and myself, Bruno Vilhena Adorno, the supervisor of this work. After this deliberation, actually after this evaluation in which members of the committee will be asking questions to the candidate, the committee will meet in a separate room and will deliberate about the outcome of the dissertation and the defense. And after that, we come back to the main room and we present the outcome of that deliberation, which can be only two options, either approved or not approved. So now I pass over to you, Juan. You have 15 minutes to present your work. Thank you.
Thank you, Professor Bruno. Hi, everyone. I'm going to present a work titled Whole Body Control of Humanoid Robots at Second Order Kinematics Under Unilateral Constraints. This presentation is organized in 8 sections. First, I'm going to present the introduction, then the objective and the related works. Next, I'm going to present some useful foundation used in this PhD dissertation. Next, I'm going to present the contributions, the results, after the conclusions, and finally, the future works. Industrial robots has been one of the main focuses of robotics, historically speaking. In these environments, tasks are often repetitive in controlled spaces. However, in recent decades, the field of robotics has experienced great growth in various fields of knowledge. New applications have emerged in educational and medical fields, also in collaborative application and home environments. This new paradigm brought new challenges and robots like humanoid robots, which are designed to perform manipulation in human environments. They often have a large number of degrees of freedom, which allows them to increase their dexterity and possibility of movement. To control humanoid robots is required to make contacts with the environment sequentially under several constraints, such as maintaining the robot balance, preventing violation of the joint limits, avoiding collisions with the environment, etc. These contacts can be cyclic or acyclic depending on whether they are periodic or not. Cyclic contacts has been used mainly for gate tasks and known environments where contacts are made on flat or slightly uneven surfaces. Aiming to perform more sophisticated tasks in cluttered environments or to increase the robot reachability, multi-contact control has been gaining the attention of research in recent years. In this paradigm, acyclic contacts are more suitable as they allow for richer movement options according to the environment. The objective of this PhD dissertation is develop whole body motion control strategies for humanoid robots with self-collision avoidance and using multi-contacts with the environment. Multi-contacts can be useful to perform manipulation tasks. For instance, consider a humanoid robot trying to grab a cup. The robot must keep the projection of his center of mass inside the super polygon in order to ensure the robot balance. In this case, the robot reachability is limited and the robot fails. Alternatively, the robot can perform a contact with the table, which increases the superpolygon and allows the fulfillment of the task. The specific objectives are the following. Define a suitable objective function in order to perform whole body control as second-order kinematics. Develop suitable constraints in order to ensure self-collision avoidance. Allow task flexibilization to release degrees of freedom, which can be used to fulfill secondary tasks. Develop suitable constraints to perform multi-contact application and general manipulation tasks. Exploit the vector fields inequality framework to impose constraints to ensure balanced tasks and contact forces with other robot parts, namely the hands. And finally, validate the proposed techniques on simulation and on real platform available in our research group macro. The acyclic contact planning paradigm requires computing the robot-based trajectory, planning a sequence of configuration that respect the set of constraints along the base trajectory, and interpolating a continuous motion between two configurations. However, dealing with those problems at the same time can lead to a combinatorial explosion. This problem has been addressed basically in two ways, using discrete searches, which usually are based on probabilistic algorithms and aims the global convergence at expense of higher computational costs. To mitigate this, local optimization has been used to trade the computation costs, but expensive of local convergence. Some works used optimization strategies to perform acyclic motions. Mordas et al. Proposed the contact invariant optimization method to perform simultaneous optimization of the contacts and task motions. Engage et al. Addressed the dynamic multi-contact motion generation by using nonlinear optimization and considering the full body dynamic model. Unlike the Mordas work, the method requires the desired contact sequence. Saab et al. Using a hierarchical quadratic programming to handle dynamic motion under unilateral constraints. The author proposed a reduced formulation for rigid planar contacts. Schunt and Katif addressed the multi-contact locomotion using the elastic strips framework. A global planar searches a sequence of contact regions based on the robot reachability. After that, a prioritized controller simultaneously adjusts the poses and the contact regions. Dates and Drake addressed the contact planning for cyclic gates using a mixed integral programming. In this case, a set of convex obstacle-free configuration space regions are pre-computed and integer variables are used to assign footsteps to those regions. Ponton et al. Extended the strategy to multi-contacts using a reduced model of the robot. However, strategies based on mixed integral programming are still computationally expensive. To mitigate this, Sunut et al. Formulated the mixed integral programming contact planning by means of linear programming. This allows taking advantage of a sparse solution at expense of optimality approximations. Collision avoidance is a fundamental requirement in robot applications. This topic has been addressed using offline or online approaches. Offline approaches usually are based on motion planning, where probabilistic methods has been widely used. However, these strategies are computationally expensive and suitable in known scenarios. Reactive methods usually require less computation time and are suitable for application within unknown workspaces. Collision avoidance usually has been handled using the task priority framework, where the overall task is divided into subtasks with different priorities. However, this strategy does not ensure the fulfillment of the lower priority tasks. Furthermore, the dynamic prioritization, which consists in changing task priorities, has an exponential cost in the number of inequalities. Alternatively, non-hierarchical formulations based on weighted least square solution has been used. However, those approaches require an appropriate weighting matrix, which may not work in general, especially for high-speed motions. Other strategies addressed the collision avoidance explicitly by using mathematical programming. which allows dealing with inequality constraints directly in the optimization formulations. Before to present the main contributions of this work, I'm going to review some useful concepts about dual quaternion algebra and the vector fields inequality framework. Dual quaternions have proven to be a powerful mathematical tool in robotics. They have some advantages. They are computationally less expensive with respect to homogeneous transformation matrices, and are more compact and also do not present representational singularities. Dual quaternions can represent rigid motions, and thanks to the strong algebraic properties, dual quaternions are suitable to model a different variety of robots. Furthermore, they are suitable to represent twists and branches and geometric primitives like points, lines, and planes. The set of quaternions extend the complex number and are defined in this way, where the imaginary units respect these properties. Dual quaternions extend the quaternions by means of an additional unit that is different from 0, but the unit squares equals 0. Unit dual quaternions represent rigid motions. The primary part contains a unit quaternion that represents the rotation, and in the dual part, here P is a pure quaternion. This is the real part of P equals 0 and represent the translation. The relation between the unit dual quaternion and his time derivative is given by the propagation equation of the unit dual quaternions. Here, this term, which is displayed in green, is a pure dual quaternion and represents a twist expressed at the body frame. The twist contains the information about both the angular and linear velocity of the body. The vector fields inequalities are differential unilateral constraints which are useful to prevent collisions between geometric primitives. For instance, consider a robot manipulator. We want to prevent the collision between the n effector and this wall. In this case, the vector field inequalities constrains the approach velocity without affecting the tangential velocities. In this framework, we required a signed continuous distance function between two geometric primitives. Furthermore, we required the time derivative of the distance function, which is composed of the distance Jacobian, the Jones velocities, and a term which is called the residual. The residual contains the information unrelated to the robot kinematics. Then we define an error distance to define safe regions. The goal is to constrain these distant dynamics. The vector fields inequality framework works with geometric primitives like points, which using our associative radius represent spheres, planes, or lines, with lines with an associated radius represent infinite cylinders. For instance, planes are useful to model walls or tables and avoid collision between them. Lines, for instance, has been used in surgical applications to prevent collisions between two robots. The main contributions of this work are the following. Extend the vector fields inequality method, which was first proposed using first-order kinematics, to use second-order kinematics. This enabled application that uses the robot dynamics. Propose a new distance function related to the angle between two lines and the corresponding Jacobian matrix. This is useful to prevent violation of joint limits or avoid undecided n effector orientations. Propose a new Jacobian related to the support polygon area of a human robot, which may be useful to potentially increase the robot's reachability and the robot's safety in terms of its balance. Rewrite the formulation of the Gauss principle of least constraints using dual quaternion algebra. This allows a more compact and unified representation. The idea is to perform whole body control in the context of multi-contact application, manipulation tasks, and cooperative manipulations in robots commanded by joint torques. A quadratic program generates the control inputs subject to constraints, as for instance, the vector fields inequalities. And then using the joint acceleration, we compute the joint torques by means of the Euler-Lagrange equation in this way. So how to apply the vector fields inequality framework to the acceleration level? This work proposes the second order vector fields inequalities. The same idea can be applied here. This is by using a vector field, the approach acceleration is limited in function of both the velocity and the distance. The goal is to constrain these distance dynamics, where the gains eta1 and eta2 must respect the following conditions. This condition is used to avoid instabilities, this one to prevent oscillatory behaviors, and this one to prevent overshoot. By using those conditions, we formally prove that the distance will be higher or equal than 0. For example, consider a robot manipulator that performs attacks in the presence of an obstacle. We define a restricted spherical region using a safe distance, and the obstacle must be keeping outside the restricted region. Then we compute the time derivatives of the error distance, which can be written in this way, where this term is composed of the safe residual, which contains the residuals and the time derivative of the safe distance. By taking the second time derivative of the error distance, we obtain these three elements, which can be used to rewrite the second order vector fields inequalities in this way, and in functions or explicitly in the joint accelerations in this way, where this term contains the information about the robot kinematics, and this one, which is called the residual beta, contains the information about the time derivative of the safe distance and the residual. This is the information unrelated with the robot kinematics. In case where the object is static and the safe distance is a constant, this term, the residual beta, equals 0, and the constraint is written in this way. This is a simulation of a robot commanded by joint torques performing attacks of controlling the nth vector position. The obstacle is static and the safe distance is a constant. On the left, the constraint is disabled, and on the right, the constraint is enabled. When the constraint is enabled, the robot prevents the collision with the object as expected. To illustrate the effects of a dynamic object, this example shows three cases. In case 1, the constraint is disabled, which means that the robot will ignore the obstacle. In case 2, the constraint is enabled, but the robot considers the obstacle as a static object. This means that the robot takes into account the object, but both the velocity and the acceleration of the object are neglected. This is simulated considering the residual beta as 0. Finally, case 3 shows the best scenario in terms of collision avoidance. The constraint is enabled and the robot knows the kinematics of the object is taken into account. In case 1, the robot and the object collide as expected. In case 2, the robot tries to avoid the collision, but the evasive maneuvers are not enough, and both the robot and the object collide as well. In case 3, the robot avoids the collision. This is expected since the robot knows the information about the object, the kinematic information about the object. The vector fields inequality framework within the dual quaternion algebra use pair of geometric primitive to prevent collision between them. For instance, the point-to-point or point-to-plane, where the points with an associated radius represent spheres. Or using, for instance, lines that associated with a radius represent infinite cylinders. For instance, point-to-point, line-to-line, but how to prevent undecided angles between two lines? The main motivation is to define realistic tasks to release some degrees of freedom of the robot. For instance, a humanoid robot performing attacks where it's decided to put a cup on a table. we can define attacks to control both the position and orientation all the times, which required 6 degrees of freedom. Alternatively, we can define attacks to minimize the distance between the robot's hand that grabs the cup and the table. In addition, we can use a constraint to keep the orientation of the cup below a threshold. So what is the idea? Given a line attached to the robot kinematic chain and an independent line, we want to constrain with a maximum angle between the lines to avoid undecided n-effector orientation or to prevent violation of the joint limits. This work proposes this function to control the distance between the orientation and the lines, between the orientations of the lines. The distance function f is bijective, and therefore controlling that distance function is equivalent to control the angle in the interval 0 to p. Using the law of cosines, the function is given by this expression. Furthermore, its time derivative is computed in function of the joint velocities by means of the line-to-line angle Jacobian and to line angle residual. To write this constraint using the vector fields inequality framework, we first defined the error distance functions in this way, where theta safe represents the maximum angle allowed between the lines. To first order kinematics, we use the vector fields inequality framework, and we can write the constraint in this way, which explicitly of the joint velocities is written by this expression. Analogously, using the second vector fields inequality, we can write the constraints in this way, and explicitly of the joint accelerations in this way. The strategy can be applied in different robot platforms. For instance, robot manipulators, mobile manipulators, cooperative manipulators, and of course, humanoid robots. In the context of humanoid robots, we can use the vector fields inequalities to take into account additional constraints as the ones that ensures the robot balance and taking into account multi-context tasks. Consider for instance, a robot manipulator performing a contact with a table. Assuming a static equilibrium, the robot balance is ensured by keeping the center of mass projection inside a region called the superpolygon. This work proposed a superpolygon area Jacobian that can be used to maximize the area of the support polygon. With a larger support polygon, the robot potentially could improve the robot reachability. For instance, on the left, the robot performs a contact with the table. Then the robot tries to toss the ball using the right hand, but fails. On the right, the robot performs the contact with the table, then performs a maximization of the support polygon, and finally perform the task to toss the ball and succeeds. Likewise, a larger support polygon area could improve the robot balance in a presence of external disturbance. Consider a robot in a multi-contact configuration where a pendulum is placed to simulate an external disturbance. On the right, we have the same robot with a larger support polygon. In this specific example, the robot with a larger support polygon keeps the balance after the collisions. So, how to maximize the support polygon? Considering a case where the robot is in a multi-contact configuration using both feet and in one hand, this work proposes an approximation of the support polygon to simplify the computation of the Jacobian. We assume static equilibrium, fixed feet, rigid planar contacts, and enough friction forces to keep the contact fixed. Then we select a contact point of the robot hand to build an approximation of the support polygon, which in this case is called SPA, such that the SPA polygon is inside of the support polygon. Then the approximation of the support polygon is composed of the convex hull of the points PA, PB, PC, and PD. The goal is to compute the relation between the joint velocities and the time derivative of the area. The area is composed of the area of two triangles and is given by this expression. Since both feet are fixed, the time derivative of the area is a function of the velocity of the point PC, which is related to the joint's velocities by means of the position Jacobian of the points on the plane. Using that relation, we find the area Jacobian. We can use both the vector fields inequality framework and the support polygon area Jacobian to perform manipulation tasks. Consider a task to touch the ball using the right hand. The robot tries and suppose that fails. Then we can perform a contact with the table after try the main task of touch the ball. For instance, in this way. If suppose the robot fails, for instance, we can perform maximization of the support polygon after performing the contact with the table and after try the main task in this way. In some cases, after the maximization of the area, the robot could fail. Then, in these cases, we can relax the hand constraint. For instance, we change the constraints that keep the robot hand fixed by the sliding contact. This allows a sliding contact, whereas the robot tries to reach the ball simultaneously. The sequence of the contact can be summarized in this figure. The green arrows represent success events, and the red arrows are failed events. The red arrows are failed events. In total, there are 4 attempts to accomplish the main task. Once we compute the control inputs using quadratic programming and the vector fields inequalities, we can use the Euler-Lagrange to obtain the torques. In the overall strategy, we use dual quaternion algebra to model both the robot and the geometric primitive. Therefore, that raises the question, how to describe the robot dynamics using dual quaternions? This work rewrites the Gauss principle of least constraint using tools from dual quaternion algebra. The Gauss principle is a differential variational principle equivalent to the Denver-Leg one that is based on the variation of the acceleration and can be stated as a minimization of a scalar quadratic function in terms of the accelerations. For a system composed of n rigid values, the scalar function is given by this expression, where this term represents the constrained acceleration, this one represented the unconstrained acceleration, and this one represents the inertial parameters. To compute the constrained acceleration, we use the propagation equation of the unit dual quaternion, which is given by this expression. Solving for the twist, we obtain this expression. Applying the VEC operator, which performs a one-to-one mapping from the set of dual quaternions to the set of vectors, and using the relation between the joint velocities and the time derivative of the unit dual quaternion by means of the post-Jacobian, we obtain the twist Jacobian that relates the joint velocities with the twist. By taking the time derivative of the twist, we obtain the constrained acceleration. We say that it's constrained because it depends on the joint's configurations, velocities, and accelerations. To compute the unconstrained acceleration, we use the twist expressed at the body frame, which is given by this expression. The primary part contains the angular velocity and the dual part represents the linear velocity. Both quantities are expressed in the body frame. Then we take the time derivative of the twist and apply the VEC operator to obtain this expression, where in the primary part we have the angular acceleration and in the dual part contains the linear acceleration. From the optimality conditions and after some algebraic computation, we obtain the Euler-Lagrange equation, which is given by this expression. This term contains the inertial matrix, which is given by this expression and depends of the twist Jacobian and the inertial parameters. This represents the Coriolis matrix and is given by this expression and is a function of the twist Jacobian, his time derivative, the inertial parameters, and a diagonal matrix that is related to the skewed symmetric matrix. And this term represents the generalized forces. and is given on this expression depends of the twist Jacobian and of course of the moments and the forces acting on the body. For instance, for a serial manipulator, the generalized forces are composed of the torques applied in the joints and the gravitational forces, which can be written in the canonical form in this way. This table shows the computational codes for an end-of serial manipulator and the comparison with their classic counterparts. The Euler-Lagrange method based on the Gauss principle or least constraints and dual quaternion algebra is as expected more expensive than the ones based on the Newton-Euler and the classic Euler-Lagrange formalism, since it's not based on recursive strategies. Furthermore, our algorithms based on dual quaternions, different from the classic strategies, works for any type of joints. Because of that, our methods are computationally more expensive. To validate the conic constraint and the second order vector fields inequalities, we performed simulation experiments. Furthermore, to illustrate the multi-contact strategy, the super polygon and the support polygon area Jacobian, we was performing a realistic simulation of the rep. We use the following quadratic program to generate the control inputs. This is the tax Jacobian. This one corresponds to the tax error. This is the damping factor, which is used to minimize the joint's velocities. And this one represents the linear constraints. We write the same strategy and second order kinematics using this quadratic program, which is this again, the tax Jacobian. This term contains the terms related to the decided tax error. And this one represents again the damping factor, and this one the linear constraints. We use ViewRep and MATLAB for the simulation and DQ robotics for both robot modeling and the description of the geometric primitive. The robot kinematic chain is composed of a 5 degrees of freedom torso and a 4 degrees of freedom left arm, which has a total of 9 degrees of freedom. The goal is to put the cap on a table while keeping the cap tilting below a threshold. To accomplish this task, the control law minimizes the distance between the left hand and the table. We use 4 plane constraints to define the target region in this way. Furthermore, we use 10 conic constraints. One of them is to keep the cap tilting below a threshold, and 9 of them are used to prevent violation of the joint limits. On the left is the unconstrained case, and on the right, the constrained case. All the constraints were respected only in the constrained case, which is expected. We performed a second simulation using second order kinematics with the same text specification. We use the quadratic programming to generate the control inputs, and in this case, we compute the torques using the Gauss principle, the Euler-Lagrange equation based on the Gauss principle for least constraint and dual quaternion algebra. These are the results of the simulation. The dotted black line corresponds to the unconstrained case. The blue line corresponds to the constrained case, and the red dashed line represents the maximum angle allowed. In both cases, the tax error is minimized, and therefore the n effector reaches the target zone. But only the constrained case does not violate the cap tilt angle constraint and the joint limits, as expected. We performed a real experiment using the platform composed of the upper body of the Popeye humanoid robot. We used Python and Rust and the quad-proc solver. All the constraints are enabled to ensure the robot safety, but only on the right, the maximum angle or orientation of the hand is enabled. We can see that in both cases, the robot minimize the distance between the left hand and the target zone, which is composed by this red square, but only on the right, the robot respects the maximum angle orientation of the hand. We repeat the experiment using the same robot platform, but in this way, instead of using one arm, we use both arms. To accomplish this task, we use the cooperative dual task space framework. In this framework, all kinematics is represented by two variables, namely the relative pose and the absolute pose. But the relative pose represents the pose of one arm with respect to the other, and the absolute pose represents the pose of a frame located at the middle of the arms. In this case, the robot is composed by 13 degrees of freedom, and we can define a task of control the relative pose, which requires 6 degrees of freedom, and to control the absolute pose, which requires an additional 6 degrees of freedom. Alternatively, we can define a task of using 7 degrees of freedom. 6 degrees of freedom are used to control the relative pose, and 1 degree of freedom is used to control the absolute distance. So in this case, the absolute frame is located at the middle of the arms, and the goal is to minimize the distance of that frame with a target plane. Here on the right is imposed the tilt constraint of the robot. In this case, in both cases, the control minimizes the distance, but only on the right, the robot respects the maximum angle orientation. We have here the results. In both cases, both control minimize the task, which is the distance between the absolute frame and the target zone. This represents the angles of the n-effector orientation. Only in the constraint case, the robot respects the maximum angle. And of course, only in the constraint case, the robot respects the joint limits. We repeated the experiment, but in this case, using a non-holonomic platform serially coupled to the upper body of the Popeye humanoid robot. But in this case, the conic constraints are used to prevent violation of the joint limits. Here we have the simulation. The task is the same, minimize the distance between the absolute frame, which is located at the middle of the arms, and the target zone, which is represented by the red lines. Here we have the results. Both controllers minimize the distance, the task error, which is expected, and only on the constrained case, the robot respects the constraints. The small violation of the joint limits in the constrained case are due to discretization effects and because the movement of the mobile robot excites the inertial parameters. We performed a simulation to illustrate the multi-contact strategy. The goal is to control the right hand of a humanoid robot to touch a target ball. In this specific case, we set 3 steps to accomplish the task. First, the robot performs a contact with the table using the left hand. Then the robot performs a maximization of the support polygon. And finally, the robot tries to touch the ball using the right hand. We use the same strategy to generate the control inputs, but here, of course, we have three different texts. So in order to accomplish the task of place the left hand on the table, we define the task error using 2 planes. First, we attach a plane on the robot hand, which is represented by this dual quaternion, where the primary part represents the orientation of the plane, and the dual part contains the distance between the plane and a reference system. We model the table using a plane as well, a decided plane, and define the task error in this way. To compute the task Jacobian, we take the time derivative of the task error, which is given by this expression, where the task Jacobian is composed by the plane Jacobian that relates the joint velocities with the time derivative of the plane attached to the robot hand. To prevent collisions between the n-effector and the table, we use 4 constraints, which in this case are point to plane primitive. Furthermore, we use 4 planes to keep the projection of the center of mass of the robot inside the support polygon in this way. To keep the robot hand fixed or to enable a sliding contact, we required additional constraints. Consider the position and orientation of the robot hand, which is represented by the unit dual quaternion XC. To ideally keep both the position and orientation fixed, we ensure that its time derivatives equal 0. On the other hand, to allow a sliding contact, we attach a plane on the robot, which is represented in this case by the dual quaternion PC. Then we ensure that his time derivatives equal 0. To maximize the support polygon, we define a tax error in this way using the area, and the tax Jacobian using the area Jacobian. In this case, we use a negative convergence factor. Since the tax error dynamics is governed by this equation, in which the solution is given by this exponential function, a negative eta implies an exponential increase of the support polygon. Nonetheless, his ground is limited by the plane constraints that define the target region and the plane constraints that keep the robot center of mass inside the support polygon. Finally, to touch the ball, the tags correspond to minimize the square distance between the robot hand and the ball. The square distance is used to avoid singularities in the distance Jacobian. The tax Jacobian correspond to the Jacobian matrix that relates the joint velocities with the time derivative of the square distance. Additional constraints were used to prevent collisions between the robot and the table, and to keep both feet stationary. This table summarizes the parameters used in the control law. The target region constraint is used only in tax 1 and tax 2, but the collision avoidance and the stationary feet and center of mass constraints are enabled in all cases. The sliding contact is only enabled in the second tax of maximizing the support polygon area. The fixed contact is used only in the tax when the robot tries to touch the ball. Here we have the simulation. First, the robot performs a contact on the table. Then the robot performs a maximization of the support polygon area. And finally, using the right hand, the robot tries to touch the green ball. In this specific case, the robot succeeds in the task of touching the ball. The maximization of the support polygon area is required in this specific case because if the robot tries to touch the ball without performing the maximization of the support polygon area after the contact with the table, the robot fails to accomplish the task. Furthermore, the contact with the table is required because in this specific case, of course, because if the robot tries to touch the ball without performing the contact with the table, the robot fails. We performed a second simulation to illustrate a case where the maximization of the support polygon area prevents the fulfillment of the task, of the desired task. In this case, the robot performed the contact, maximized the support polygon area, but in this case, the robot fails. And in that case, we can use the last resource, which is relax the contact constraints of the left hand with the wall and allow a sliding contact to simultaneously minimize the distance between the right hand and the ball, whereas the robot perform a contact with the wall. But this simulation shows a case where a higher support polygon prevents the fulfillment of the task. This is not surprising because the proposed maximization of the support polygon area does not ensure a better robot reachability. To conclude this presentation, this PhD dissertation extended the vector fields inequality framework to second-order kinematics with a formal proof that shows that the strategy ensures collision avoidance. This work proposed a novel singularity-free conic constraints proposed to limit the angle between two lines. Furthermore, this work proposed the new Jacobian useful to prevent violation of the joint limits or avoid undecided n-factor orientations, and a new Jacobian to maximize the support polygon area, which may be useful to potentially increase the robot's reachability and the robot's safety in terms of its balance, although the proposed maximization of the proposed strategy does not ensure a better robot reachability. This work rewrites the formulation of the Gauss principle of least constraints using dual quaternion algebra. This allows a more compact and unified representation. In addition, the formulation based on dual quaternions and the Gauss principle of least constraints allows theoretical connections with other strategies based on dual quaternion algebra developed in our research group. Furthermore, this work explored connections with other strategies as the Gibbs, Appel, and Keynes equations. And we explored additional constraints in the Gauss principle or least constraints to model, for instance, non-holonomic robots. The approach based on vector fields inequality requires an environment modeled with a sufficient geometric primitive and it's not free of local minima, but provides reactive behaviors. As part of this research, we published a paper in the robotics and automation letters, and we submitted a second paper to the Journal of Mechanics and Robotics. Future works will focus on the implementation of the second-order vector fields inequality on real platforms and explore multi-contact applications using the proposed strategy, considering the contact forces and friction forces in the computation of the support polygon area, which was neglected at the moment, and enable non-coplanar contacts and dynamic stability, exploit the inequality constraints, the Gauss principle or least constraints to model different broad platforms, and using the proposed strategy to modeling a variety of different robots and using the hypercomplex forms of the dual quaternions in the Gauss principle. In this work, we used only the matrix form of the dual quaternion algebra. I would like to thank the Brazilian agencies for their financial support during these 4 years. And I would like to Professor Bruno and colleagues, especially the one supervised by Professor Bruno. And thank you.
Thank you very much for the presentation, Juan Jose. Now it's time to pass to the other step of this evaluation. So I will first call Dr. Abderrahmane Kedar so that he can do his considerations. And please, Abderrahmane, the stage is yours.
Okay, thank you very much. I would like to thank you, Bruno, and thank you, Juan Jose, for inviting me for defense. First of all, I would like to congratulate you for the presentation, which is extremely clear, and also for your manuscript, which is very nice. Unfortunately, I didn't have time to go into all the equations in details, but I think I understood really the principle behind, and it's frankly speaking, it's a very nice piece of theoretical work. Obviously, I am aware of all the problems of that one might face in the planning and the control of complex humanoid robots or complex robotics platforms at large by doing multi-objective tasks and in the task space. So, so I highly appreciate your dedication to prove the things and to try and to push the idea of using dual quaternions for modeling the dynamics and also modeling several aspects of the control and also of the planning, if I may say so. I think that my role is also to ask you or challenge you in a few questions with respect to your approach and to see how, if I'm really convinced that I will change a little bit my framework and use your tools to control our own platforms. And for that, I need a few clarification from you that might probably bring additional maybe benefits for the method. And I will start first by asking you a very simple question: how long did it took you to do this PhD thesis? I mean, the whole PhD work. How much time did it? I mean, did it last for you to perform or achieve your PhD?
Excuse me. Would you repeat the question? I have some troubles here with the sound. I'm so sorry.
Okay. So my first question was how long did you take to do your PhD?
Well, almost 4 years and 3 months, I think.
For 4 years. Okay, that's very cool. So let's start by the fact of the aspects of the distance, okay, and the computation of the distance. So the first question that come to my mind, because it wasn't clear in my script, is your distance function applies for general mesh robots, or the form should be very simple, like a line, sphere, and cylinder? So can it extend to any kind of polytop or polyhedron or a mesh, okay, that represents your robot exactly without the requiring of simplifying the form of your robot?
Well, of course, the strategy requires, the idea is to compute the distance between two geometric primitives. In this case, the idea is to model the robot using the geometric primitive. However, here you have a mesh to model your robot. Probably there is an algorithm that gives for you the 2 points between the mesh, the two nearest points. So in that case, you can use the distance between 2 points, for instance, model obtain the distance between 2 points. But in some cases, it's useful to model the robot using an additional geometric primitive. For instance, you have an obstacle, a cylinder obstacle. In that case, a line with an associated radius is more interesting than giving a mesh, for instance. But of course, in that case, when you have a mesh, you can use the distance between 2 points and obtain the distance Jacobian between them.
Okay. So because I didn't see in your work we have worked on these aspects. We had like a throw paper with Adrien Escond, Sylvain Miosek, and also Ben Aleg and myself on this distance computation and the use of the general mesh and the use of a bounded mesh. The problem with the general mesh is that the distance is not continuous. I mean, the derivative, if you use a mesh, when you compute the points, okay, it doesn't give you a derivable distance function if it is not smooth. I mean, if the surface is not necessarily smooth, but at least C1 derivable. So then for you, the approach can be generalized as far as you can have the distance, in fact, that is given to you by using any bounding mesh that ensure to you to have a distance, to have like we call them witness points that are derivable. Then the other question comes into what is really the benefit for me of modeling this distance using quaternion, because it's at the end it's just a distance, and if I have a mesh, I will just compute this witness point and I can compute the Jacobian. We do it, in fact. So in our paper. So I didn't grasp really what is the benefit of using dual quaternion in this particular case.
Well, we use dual quaternions to represent several things. In this case, the robot modeling, the rigid motions, the description of the text, and when we use that representation, we don't require to set to extract parameters of metrics to, for instance, apply to control strategies. So since the dual quaternions allow the representation of a different variety of things like the geometric primitive, I think that it's a great opportunity to use the tool to abstract the description of the text. And also it's a efficient representation. And as was mentioned, of course, we can use vectors, but a question that arises in that case is why to use a different representation, since you can use the same for all you need.
No, okay. So then, in fact, the dual quaternion algebra doesn't have any direct impact in the way you compute this distance. In fact, the distance is an independent aspect. It has some few benefits on how you would compute probably the Jacobian and things like that, but not necessarily. And so far, any algorithm that gives you a C1 witness point on your robot can work. Then I can probably send you a few of the material we have used for having C1 distance without the necessity of modeling the robot as a sphere or very simple shapes. Because the problem with these very simple shapes is that they are, in fact, they are too conservative sometimes to do, especially multi-contact. Okay, if you start doing multi-contact and you model your robot as a sphere, then you can do really nothing. Okay, because of the range of motion is really highly compromised by the fact that you are using high, really gross approximation of the shape of your robot. Okay, so this part is clear. Thank you very much. The other part that I didn't really understand well in your distance function is this xi, which is called the safety time something. I do not really see what it is used for. Is it like a safety distance? So maybe you can go back to any slide where you write the distance with respect to this C function. Zeta for it. Sorry, zeta. It's a zeta function that you call zeta safe in the computing of the distance, in the computation of the distance. And I do not really grasp. Yes. The D safe. Okay. So the residual, what you call the residual. What is it exactly? This residual.
Well, the residual is a term that appears in the case, for instance, the object is not a static entity. For instance, if I have a point that is not a state, it's a dynamic point on the robot, the residual contains the information about the velocity of the object. For instance, okay.
Yeah, okay, I get your point. But in fact, it's very easy to get rid of that by considering the relative motion, because you don't need to take explicitly into account the velocity of the other object. If you write your distance in the robot frame and consider simply the relative motion instead of, but I understand. Okay, I see why it's here and what is its role. So thank you very much. Yeah, for this one, I totally understand it now. So the third point, which is mostly a remark that I will invite you to consider after, is when you speak about the support polygon when you are in multi-contact. Okay, so you didn't mention how do you obtain this support polygon for multi-contact. I mean, do you have an idea how this polygon is computed, or how do you compute this multi-contact balance?
Well, yes, some in the literature, some papers, the super polygon is computed assuming, for instance, is static equilibrium. In that case, we model the robot using a convex model. For instance, the center dynamics of the represented the robot using the center of mass, and studying or applying the force and moments in order to get a static equilibrium. Using that strategy, the super polygon is composed by the convex half of the robot of the contacts points.
Okay.
But in this case, assuming, for instance, coplanar contacts.
Yeah, well, you are in multi-contact. You cannot assume really coplanar contact because otherwise it's not really multi-contact. So yes, so this is what was not clear in your thesis, and I can inform you. You are in a quasi-static. We compute this polygon by using brittle algorithm. Okay, that allows you to have an approximation through projection method. The computation is extremely very fast, and yeah, you can use this the work of brittle that we have implemented here in our lab, and to use this polygon, okay, for multi-contact shapes. It's still a polygon when you are in a static equilibrium, but when you start moving, this polygon is not a polygon any longer. It becomes a polytope, and this polytope, we have also provided algorithms to compute it. So I just want to make you aware that in fact in multi-contact, the balance equilibrium in statics is not the convex hue of the contact points, okay, but it's still a polygon, okay, in quasi-static, but that needs to be computed. You cannot just take the convex as in your slides, and if the robot is moving, unfortunately, it's not a polygon any longer, okay, and you have to have set value points, and this is the reason why I was thinking, oh, maybe this dual quaternion have probably a nicer way to compute this distance, these balance regions, but it wasn't the case for the work. Then for I will try to be not too much. I'll speak just a few things that pop up to my mind when I see your slides. In the page 88. I see that you are using you reformulated the Gauss constraint for the Gauss principle for least constraints by using dual quaternions, okay, for formulating the. By the way, just as a remark, because I saw in your thesis that you wrote in equation. I will get to it soon. In your equation 5.41 in page 56, okay, the Gauss principle of these constraints, and it writes basically like this, the inertia matrix, etc. But please notice that it doesn't apply only for equalities, but it applies also for inequalities. Okay, and the Gauss principle, you can minimum. In fact, what the Gauss principle says, and this is the reason why we are using it. We used it in a paper that we published in ICRA 2000 with Stéphane Rodon. We use it because we were interesting to formulate this in how to say, formulate this as inequality constraints to take into account the fact that the robot is sliding, the fact that the robot is doing some other aspects. And I just let you know that this A Q dot dot equal B could, in the general way, right, you can keep 5.41 to include also B or C Q dot dot less equal to another thing. So inequalities are also accounted, and I think the power of the Gauss least principle is also to handle inequalities in the same way. And then if you consider inequalities, it means that you consider aspects where you have also kind of sliding, then you can. Do you think it's just a simple question, which I know the answer? Do you think that your dual quaternion would have any problem to formulate also inequalities or not?
No, not problem at all, because the constraints are writing in function of the control inputs of the joint acceleration.
So my concern is, frankly speaking, why did you use the dual quaternions to reformulate the dynamics fully? Because you said something, and unfortunately, it's not totally true. I think the most powerful algorithm that exists so far until now to model the dynamic equation of motion is Featherstone. And the Featherstone algorithm is the fastest, basically, we know, and it's what we are all implemented. And it's not true that it doesn't apply for any kind of joint. It applied for basically all the joints. So the question I'm asking you is why probably you couldn't consider a hybrid approach. I mean, using probably Featherstone algorithm for computing extremely fast the joints that are easy to compute, and probably use dual quaternions in probably few joints that you think are problematic, like ball joints, for instance, and most importantly, to add joint limits for this. So did you think about having more of a hybrid approach instead of full dual quaternion based dynamic modeling, because clearly you are not competitive with the state of the art in terms of computation? So why you didn't think about probably using a hybrid approach?
Well, at the moment, we are interested in theoretical aspect of the dual quaternion algebra. I'm not interested, or we are not, as the group, research group, in the case of higher computational or efficient algorithm. So I think that I don't have problem with a hybrid approach, but I think that elegance of the method in the description is use the representation, or using a unified representation. I think that is a thing that we appreciate. But I would say, respecting to the comments about the any type of joints, well, we are, I don't know how I express or I say in the wrong way, but I was comparing the algorithm with these strategies, which in this case, the computational costs were computed specifically for rotational joints. In that case, in this specific case. So we compared our strategy using dual quaternions, where works for any type of joints, and we compared with using two strategies, classic strategies, that where the costs of that strategies were computed only for rotational joints. But of course, that strategies can be extended to any type of joints, but this specific code is specified only for rotational joints. That is what I would like to say.
Okay. Then my other question is very simple. Do you remember which physical engine you used on the VRAP simulation that you presented?
Excuse me.
What is the physics engine that you use with VRAP for your simulation?
We VRAP have several engines, but we have good results using the Vortex.
Vortex, okay. So that was my question. I just wanted to make sure what is, because the simulation seems extremely stable. Then yes. I assume yes, you have used Vortex. Okay. So So in fact, the conclusion you stated is correct, that increasing the balance region doesn't increase the reachability of the other joints. In fact, it even decreases them. Okay, because if you want to be very, very stable, then you constrain yourself a lot to use the others. And so I was a bit surprised to see that you thought that by increasing the balance region, you would increase the reachability of the robot. It's totally not true. I mean, and what is totally true is that by doing so, you will really reduce the reachability space, okay, for the robot if you increase the balance region. So that's why you shouldn't necessarily think about increasing the balance region, but just have a balance region which allows you to do the task, and also make sure that this balance region is computed dynamically, because in fact it cannot be constant or each time. It has to be computed with the task. My last question will be about the friction, because this is what I didn't see in your work. How the friction constraints are integrated in your framework? Are they integrated? And if so, how do you integrate the friction constraints in your modeling, in your QP control?
Well, at the moment that force constraints were neglected, but future works will be focused on that. Actually, I am reading some papers of your research group where you are co-author. Well, in that case, well, you know better than me. I am using the strategies to include the forces frictions are based basically in taking into account the reduced models dynamics or full dynamics model of the robot to take into account forces. In this case, we use only the strategy which only use it for first order kinematics, and the kinematic models neglect the forces acting on the system. So extending the strategy to include the dynamic models, to include the friction force, I think that is the way.
Okay. So I would like to thank you again for this work. I will give, of course, the stage. I have plenty of other questions, but I think these are the most important, which is useful also for you. And if in the course of the discussion, pop up again to my mind, I will tell you first. But I really like the fact that you did a lot of effort in trying to model everything, and to show that in fact it could be a powerful tool to extend the second order dynamics, and that is really very amendable. Thank you very much.
Thank you.
Thank you so much for your considerations up there. Now I will pass the stage to Murilo Marinho for him to do his considerations. But before that, sorry, Murilo. Juan Jose had asked me before if we could have just a 5-minute pause or even less, because he's drinking a lot of water. So I think he needs to go to the bathroom.
Pardon me. Thank you so much.
Okay, just a couple of
Yeah,
minutes.
no problem. We can understand that the stress is and the stress, and also the weather probably in Brazil would require him to drink a lot of water. No problem.
Well, before starting the defense, I said to him that if he continued to drink water as he was doing, so he would have to use the water bottle not only as a source for water, but as a destination afterwards.
I can understand. Yes. So Juan Jose is now located in Brazil, right?
Yes. So one thing that I'm going to do some considerations and present some remarks at the end of the presentation in the defense. But so yes, he's been in Brazil for 6 years and a half now. So he did his master's there, so for 2 years. And then he started the PhD program. In Brazil, the first year is completely dedicated to courses, like in the US. So research-wise, it's really just 3 years, actually.
Okay, that's really good. Yeah, it's a lot of amount of work.
Okay, are you ready, Juan?
Yes, I am.
So yes, so please, Murilo, you can start your considerations.
So I've been following your work since you graduated your master's, and I can tell that you work very hard, because it's pretty impressive the amount of stuff that you were able to do in this time. And I think that the quality of the thesis is very high. And I did make a few comments every other page because of some, let's say, you misspelled something, or there was some conjugation that was probably not correct. But in general, very, very good. And the presentation was also very well done. And I can tell that you practiced a lot. And there is a slide that I liked a lot. I think it's slide 23. I'm not really sure, because I decided to write it down after it just passed by me. Probably not that one. The one that you show about how the VFIs work, I think is one of those animations that has a robot and you have some arrows. Maybe this one. Can you play the video again? Yeah, maybe this would be slide 25, I guess. I think this would be really good to explain how it works to a lot of people that I have tried to explain 100 times and they never understood. And I should probably have done something like this. So that was pretty cool. So I had just a few questions here that some of them about the thesis and some of them about what was done, but nothing too complicated, I think. So there is a part here in the thesis that you describe. I think is this section, chapter 2, section 2.1, the multi-contact control of humanoid robots, discrete searches. And I just felt that in the end of this specific section, you could mention that, if I understand correctly, you don't use any this kind of technique in what you're doing the thesis, right?
Right.
Yeah, right. So yeah, just because I felt it was just not said here. So for example, in the next one, in 2.2, in the end, you explain how that's related to your work. So I think it's just a small thing that I noticed. What else? So everything is marked here. Blah, blah, blah. So this is super small. I can just send you that PDF afterwards. So the second part, let me get there. So it's already about the simulation in which you want to maximize the support polygon. And I just wanted to ask you, but I don't have the answer. Just wondering why that was the case, like how difficult it would be, because maybe it's related to slide. I don't know. Is that simulation in which the robot has to increase the maximize the support polygon? I don't know which slide that one was, but in the thesis is page, yeah, that one. It's page 36. And I just wondering because for the feet, you're using they are like a rectangle or a square. I cannot tell from the picture, but you use several points in the feet like as a square. But from the hand, you use the center instead of 2 points for the hand, for example. So what is the reason for that? Is it much more complicated if you use several points for the hand?
Yes, the idea was to find the Jacobian area in a simplified way. So using a point allows, for instance, to model the support polygon or approximate the support polygon by means of two triangles, which it's very easy to compute the area Jacobian. Of course, right. This is conservative.
So if let's say you wanted to, because I was just looking at the way that it was done, it's just like you mentioned, right? You have two triangles, but let's say you want to make three. Would it be much more complicated to compute again, or not so much?
Well, it's in fact a little bit more complicated to express the time derivative of the area in function of the joint velocities.
Okay. And another probably easy question, maybe you check this, and so in equation, I think 4.43, there is something in the denominator that I was just wondering, is there any case in which it could be zero, or no way?
Excuse me, can you give me the page, please?
Page 37. 37. But you don't need to answer me now. I mean, I just some food for thought, just in case it could be, because every time I see anything in the denominator, I just wondering if it can be zero or not.
In this case, okay, denominator is A and B, right? A and B.
The 4.43, so you have the square root of 1 minus u squared. So is there any case in which u squared can be 1, or no?
Okay, so wait a minute here. Where is u? Define it. No, now because the point depends of the point A, B, and C, but the point A, B depends of contains a fixed point on the fit, so that case is not going to happen.
Okay.
That case.
Okay. I mean, if you say so. And so the same applies for the other, for equation 4.45, if there is any chance that, probably those not, right? Because A and B can never be zero in this case, right? I'm guessing. Because of the way that you are defining the triangles, A and B, the length of those can never be zero, right?
Yes, the C, the C, it's composed of 2 points which are fixed, the diagonal points in the fit, fit. So.
Okay, so let's see for the next question here. So for the constraints for the feet, and this I'm just asking you out of curiosity, it has no judgment whatsoever. So in page 42, so for the constraints for the feet, you mentioned that you had two constraints, right? One for the relative pose, and one so that the absolute orientation would not change. Is that correct?
Correct.
So is there any chance that the absolute position changes in this scenario?
But assuming that the robot is not perturbed by the external disturbance, so assuming that the robot is not collide with some obstacle, and by ensuring only the absolute position, the absolute orientation of the feet and the relative pose keeping zero, ensures that the robot feet will be fixed.
Right, you cannot just slide for any reason, right? That's impossible. Okay.
Yes.
Cool. What's the other one here? So there is another question about that simulation where the robot is holding a cup, and again, it's just out of curiosity. What is the reason for the two hands to have that constraint, that relative pose constraint?
Excuse me, can to give me the page, please?
It's, I think, page, no, not this one.
You mean the simulation of we using the both arms of the robot?
It's page 74. Is that experiment with the robot? I think you already also did simulations. I'm not really sure. Because the robot is holding the, like a plate or something with one hand, but you have
Yes.
You have both hands constrained in to have this relative pose constraint. Just wondering why that's the case. Does it make the motion of the robot easier, or?
The page 74 is presents a snapshot of a simulation using the left arm only, right? The 74. You
Yeah,
mean
yeah.
The another simulation using both arms, maybe page 76.
Let me see. So in 74, in 76, yes. In 74, you constrain only one arm. The other one is not
Yes.
constrained. Okay.
Exactly.
So in 76, you have this relative pose constraint. I'm just wondering why that's the case.
Yes, it's to ensure the robot safety, because the idea is simulate that the robot is grasping a plate using both arms. So you need to constrain the relative pose to keep the pose static in order to manipulate the object, because you can broke of the robot or the object to be manipulated if you not control the relative pose between them.
Okay. Because I think in your presentation you showed one snapshot that actually the robot was kind of holding an object with both hands. So I think that one was the reason, right?
Exactly. Yes,
Okay.
I think this is this one.
Yeah, exactly. So when I saw this, I was like, oh, okay, now I get it, because the robot was only holding it with one hand. But I understand the point. So in fact, it would just be the same as holding a bigger object, but you use this one for the experiment, right?
Exactly.
So in maybe too small of a comment, but just wondering. So in page 85, in the beginning of the section, you mentioned that we perform simulations of a 7 degree of freedom robot manipulator, which are implemented on MATLAB. And in the end of the page, you mentioned that those things were implemented in Python. So I was just, maybe I misread something, or in page 86, for example, you show the speed of the computational speed, right? So that it was using Python, I suppose, because super fast.
Exactly. Yes.
Right.
In MATLAB only was the simulation that it's illustrated in figure 6.20 that shows the mean percentage error. The mean percentage error are implemented on MATLAB, but the computational time, which is the related to the figure 6.21, is on Python and the Cube Robotics.
Okay. So in the first one is because, like you mentioned in the text, you trust a lot the MATLAB implementation, so you can check with the state of the art, let's say, and then for the computational speed, MATLAB would be so slow that it would not be fair. So you use Python. Is that correct?
Correct.
Cool. Okay, maybe another small comment though. In page 86, so I understand that it was kind of interesting that all the things that you had to do to be able to compare this using VRAP, because VRAP did not give you enough information. So it was pretty amazing how much work you had to put to be able to do this comparison, and you still went with it. So it's nice. So just a super easy question for you, because you implemented everything anyway. So the filter that you used in this block diagram, you mentioned 2 filters, right? in page 89, figure
80.
6.23. So you mentioned it's a Butterworth filter, if I'm not wrong.
Yes.
Yeah, with the discrete. Is the filter the same, or did you have to somehow tune them for those two blocks?
It's the same. It's the same.
Okay. Cool. So did you have to tune the filter itself, or did you basically choose one and then you went with it?
We choose the Butterworth filter
Yeah.
because presents smoother responses, but we use it. We set the filter adjusting the gains and the order of the filters. But in fact, was a hard work, but with a teamwork in collaboration with Federico Afonso and Bruno, of course, because it's a working for a paper of 3 authors. So it's
cool. And I never used this. What do you call this? CMC, the coefficient of multiple correlation. So probably keep an eye for that. It's pretty interesting. And okay, so I guess I went through the whole thesis. So I do have some very small comments, but if you don't mind, I'm going to send you the PDF, the one marked with the iPad. And I really enjoy your work. The presentation was really great. And that's it. Thank you very much for inviting me for your defense, and I hope I can see you soon here in Tokyo.
Thank you.
Thank you, Murilo, for your considerations. Now I hand over to Vinicius. Please, Vinicius.
Okay, thanks. First of all, can you all hear me properly? Because I had to switch from my computer to my smartphone because I was having some problems with my connection. It is okay?
Yes.
It is.
All right. Okay, fine. So first, I would like to thank you, Bruno, and also you, Juan, for the invitation. And I have been following your work since your qualification. And I said it before in your qualification, I will say it again. The document is very well written, and all the Bruno students put a lot of effort into the images. So the illustrations are very interesting and helps a lot in understanding the concepts. So it's a very, very good job, right? And of course, it stayed the same in your final version. So your final version also has this property. The experiments are very satisfactory, and it's pretty clear to me that you put a lot of effort. I saw you a lot of times in FMG working. So again, a very good job. And overall, I would say that this is definitely worth a thesis, and this is corroborated with your publication in RL, which is a very good journal. So for me, you meet the demands, the requirements for having a thesis. And the thesis topics, it's very interesting for me, especially the part of using constraints, using optimization for computing control actions, which is something I also work. So I have some comments and some questions about your thesis. So first, a comment in page 15, where you provide your first optimization problem, equation 3.1. So essentially, you always consider that lambda is greater than 0, right? Or do you have some examples in which you use lambda equals to 0?
Excuse me, can you, I missed the page, the number page of the...
It's page 15, equation 3.1.
3.1.
Yes, in which you give the optimization problem. So essentially, you always consider lambda greater than 0, right?
Yes.
So in that case, your optimization problem is strictly convex and the solution is unique. So you don't need to put the symbol inside. You can use equality, as long as, of course, your feasible set is not empty. Because you write the inside symbol because you're considering that you can have multiple solutions, right? In general.
Yes.
But when you have lambda greater than 0, it's a strictly convex problem. So as long as the feasible set is not empty, you can just use equality. So
okay,
you simplify your equation. The same can be said about equation 3.2 and 3.3 and so on, as long as lambda is greater than 0. Okay, all right. Now in page 22, where you discuss your strategy for collision avoidance of second order, 22. All right. Equation 4.6, you provide an inequality that you have to put into your optimization problem to guarantee collision avoidance. And one of the major difficulties in using this inequality is guaranteeing that it will be feasible, right? Do you agree with me?
Yes.
Because as long as it's feasible, you prove it that it's able to avoid collision. But how can you guarantee that at every step it's going to be feasible? This is a huge theoretical challenge. I don't know if some articles, there are some results, at least some definitive results about that. Did you thought about this? Did you have this problem in practice? I mean, maybe sometimes we were using this approach and suddenly the optimization problem didn't have a solution. So what can you say about that?
Yes, in fact, it's a challenging topic. In this world, only we assume that the robot, the optimization is feasible, then the robot have the enough power to prevent the collisions, whatever the velocity and acceleration of the object. Some words addressed the strategy to take into account the feasible solutions, but it's not really a topic that was developed in this PhD dissertation, and it's a topic that I'm interested in working. But in this moment, I really don't know how to take into account the feasibility in the optimization formulation. It's an assumption that is going to be feasible, but really I don't know how to take into account that feasibility.
Okay, did you have this problem in practice?
In practice, no, but in simulations, okay, in simulation we have some troubles because the robot required, for instance, two constraints were infeasible between them, especially the ones that is to impose it to minimize the joints velocities in the second order of kinematics, because the quadratic program and second order kinematics only minimize the joint acceleration, but does not ensure the minimization of the joint velocities. Because of that, we use an additional constraints to minimize joint velocities, but that constraints was conflicting with the second order vector fields and inequalities. In that point, we used hierarchical quadratic formulations to put the secondary tags in a lower priority of the minimized joint velocities, but concerning to the feasibility about the joint accelerations, it's a topic that I'm really I am interested to working on, but I don't know how to take that feasibility in the formulation.
Yes, I think this is the major problem now with this approach. I mean, how to guarantee that given that you start in a set of the state space, which is feasible, you will always stay in the set and the optimization problem will always be feasible. For the first order analogous inequality, which Bruno and I worked in 2016, it's easy to guarantee. Okay, as long as you start in the set, you can always stay in the set and it's always feasible. But for the case of the second order inequality that you give, I don't know if someone already gave a definitive answer for this problem. I made some research about this a while ago, and I found partial results, but not a definitive answer. So definitely it is interesting, and I would expect you to comment about that in your future works, because I don't think you mentioned that in your future works, right? And I think it's the most important problem now. How can I guarantee that this is always feasible? Or at least which sufficient conditions I can give in order to guarantee that this will be always feasible at every step? Okay, of course, you need some considerations. For instance, the obstacles can't move very fast and so on. But all right, I would think an analysis in this direction is very interesting. Okay, so right, that is it for page 22. And now for page 29. Page 29. Okay, page 29, 2 comments. First, the equation that you give in 4.25, I use this function a lot with my students in the undergrad lessons I give in robotic manipulators for controlling the orientation of the end effector. It's essentially the same function as you provide here. But just a comment, I have been using the exact same function as a task function in order to control the orientation of the end effector, right? So it was nice to see it here in your thesis as well. And also about this, in equation 4.26, I don't know if you noticed it, but the Jacobian, it's null when the two vectors are parallel. You see, in equation 4.26, when LZ equals to L, it vanishes. I didn't know if you realized that.
Not.
Okay, but that's not a, when you use pseudo inverses, they can handle that and it works flawlessly. So it's a theoretical problem, but in practice, I have been using that for a long time and it works very well. Maybe it's just a matter of commenting something about this, right? When the two lines are parallel, you have a problem. When the two vectors you want to align are parallel, this task function has a singular Jacobian. But all right, it works. It works very well, as you noticed. Also, about this page 22, I would say, that's my opinion, of course, you can disagree, that lemma 4.2 and proposition 4.1, proposition 4.2, they are trivial. I mean, proving that this function is bijective, this can be done by inspection, in my opinion. It's just my opinion. So if you take into consideration my opinion, maybe you can just simplify and say, it can be seen by inspection that this function is bijective. In this, you need, of course, the sets, the domain and codomain, in order to make this affirmation. But for me, it's a very simple observation. But it's just a comment. Of course, you are free to decide whether or not to take this into consideration. All right, this is it about page 29. Okay, page 31. You use the Plucker lines in order to generate constraints to avoid joint limits, right? You use everything you have developed so far in order to generate constraints to avoid joint limits, right?
Right.
So I was wondering, why not use something easier like Q minus Q max, for instance, in which Q max is the maximum joint limits you want, or Q minimum minus Q? Why do you have to use this more complex framework to guarantee joint limits, or just not use this task function, this inequality task function, Q minus Q max, for instance, in order to guarantee that Q is never greater than Q max?
Yes, in fact, there are several ways to take into account joint limits without computing a Jacobian, for instance. But in this case, it's just for illustrate the application of two lines, because the main idea is to prevent violation of the end effector orientation. But since the problem is the same for the joint limits, we can use as well to prevent violation of the joint limits. Of course, we are required to compute additional Jacobian, but a feature of this strategy is that you required one constraint per joint instead of two constraints for the lower and the upper bound of the joint. But of course, this strategy for prevent violation of the joint limits requires compute additional constraints. I honestly, I don't know if it's the best scenario, because maybe for large degrees of freedom robot, compute that Jacobians for its joints maybe can be computationally expensive, but the idea is only for illustrate that the strategy works not only to prevent undecided n-effector orientation, but as well to prevent violation of the joint limits. It's for illustrate.
All right. Okay. Right. Now in page 32, I was going to comment about the geometric distance between more general objects like cylinders, but I think Abraham already said essentially what I wanted to say, so I will jump that. We'll skip that. So, in page 42, there's something that bothers me. Right. In equation 4.53 and 4.54 and 4.55 and 4.56 as well. I mean, you want the relative and the absolute position to be constant, right? That's why you create these constraints.
The relative pose and the absolute orientations.
Absolute relative. Okay. You want them to be constant, so that's why you equal it to 0, right?
Right.
But maybe there are some drifting problems due to numerical integration or do some noise that cause these to deviate from 0. So it wouldn't be better to add the right side a control term, a proportional control term to the error in order to correct these deviations. Because when you want something to be equal to 0, you can, just differentiate and equal it to 0. Okay, you want something to be constant, you can just differentiate as you did and equal it to 0. But in practice, there can be some drifting errors that deviate this from 0. So you need some correction term in order to return it to 0. I don't know if I was clear in my...
Yes, it was. In fact, the drift problem, which arises because the discretization effects, for instance, can be a problem here. Of course, we can use instead impose the dynamics to ensure that that constraints will be satisfied. But in this case, in this specific case, the idea was to show the constraints ideally. And of course, in the simulations, the problem was not visible because the constraints, the friction force between the feet and the ground. So the drifty was minimized because the additional friction force, but yes, I agree, the drift problem can be a problem here.
Okay, perfect. Your explanation was perfect. Because of some physical interactions between the robot and the environment, it isn't necessary to have a correction term here. But if you wanted, for example, the hand of the robot to be constant and there isn't anything, any kind of friction and preventing it from moving, you need a feedback term, right? Because otherwise it can drift. There isn't anything physically preventing the move of the hand of the robot to move, right? But in this case, there is friction there, so it isn't necessary. That's your explanation. Okay, right. Okay, now moving on to page 45. About the Kalaba-Odowadia equation. There is something that bothers me as well, because you said in your conclusion that this approach is more expensive than the other approaches. It's cubical and the others are linear. But you can handle acceleration constraints, right, directly. And in the other cases, if we had these constraints, if you try to use Euler-Lagrange with this constraint, there could be problems in order to formulate. But there's something very important here, and I would like to see if you agree with me. All the constraints that you can write in as linear in the acceleration, a times x2 dot equals to b, it comes either from an holonomic constraints that you differentiate twice, for example, in subsection 5.4.3, you have a holonomic constraint, 5.54, and you differentiate twice in order to obtain acceleration constraint, right?
Right.
So, okay, an example of holonomic constraint that you artificially transform into a linear constraint in acceleration. Or do you have a Pfaffian constraint that you differentiate once to obtain an acceleration constraint? This is the example given in subsection about, let me see where it is. When you speak about the unicycle constraints, where it is.
Maybe
Okay,
page 56.
Yes, page 56. You have a Pfaffian constraint and you differentiate once in order to obtain acceleration constraint. My point is, if you have a holonomic constraint or a Pfaffian constraint, you can handle it very easily in the Euler-Lagrange formulation with Lagrange multipliers, because you can easily solve for the Lagrangian multipliers, right? Except when you have inequality constraints, but that's another point. When you have equality constraint, it's very easy to solve for the Lagrangian multipliers. And I can't see any example, any physically coherent example in which you have a constraint as ax2 dot equals to b, which doesn't come either from a holonomic constraint differentiating twice, or from a Pfaffian constraint differentiating once. So I don't see why one would use this. I don't know if it was clear because it was kind of complex explanation, but my point is, every physical constraint that you have, physical constraint, either holonomic or Pfaffian, you can just handle using Lagrangian approach. And if you have a constraint like that one, it comes artificially. You have to differentiate twice or once in order to obtain it. So why? I don't know.
In fact, when you use, you can use a different principle of mechanics to write the dynamical description of a system. If you use the Lagrange, the Lagrange of a robot modeling, of course, the principle is designed to only accept non-holonomic constraints, right? In the case where you have non-holonomic constraints, you have to do additional steps, like for instance, include the Lagrange multipliers in order to get the solution. The same can be done using other principle of mechanics, like the Keynes equation of the Gibbs-Apple equation, where the principle works for holonomic and non-holonomic constraints as well. Of course, in case of non-holonomic constraints, in some principle like the Keynes equation of the Gibbs-Apple equation, you are required to set up additional system of coordinates called quasi-velocities in order to take into account non-holonomic constraints. You have a system and you want to model using the Gauss principle of least constraints, and the system is subjected to holonomic constraints. The solution it's equivalent to the, actually all the strategies are equivalent between them. So yes, you have model of one dynamical system, you have the same results using another principle. The case of the Gauss principle is that maybe, I don't know, but in future works, I want to work on additional constraints, but not only equality constraints, but inequality constraints for model, for instance, contacts, or for instance, joint limits as well. In that case, with inequality constraints, the modeling using the Euler-Lagrange method or the Keynes equation or the Gibbs-Apple equation, it's I don't know if possible, but at least it's more complicated, because in this case, the formulation is, the problem is formulated as a minimization problem. So in this case, the constraints can be applied directly in the optimization formulation. So because of that, I think that the Gauss principle have some features that are interesting for future works. But of course, for a system subjected to holonomic constraints, the equations are exactly the same.
Yeah, Okay, my point is that for equality constraints, I don't see why, because these equality constraints, I also made some research in other papers, not only your thesis, and all the acceleration constraints that I saw, they come from either a holonomic constraint differentiating twice or from a Pfaffian constraint differentiating once. In that case, you can use very well the Euler-Lagrange approach and obtain the same equations, of course, and with the same complexity, because you also have to invert a matrix in order to obtain the Lagrange multipliers. So it is the same. In the case of inequality constraints, then I don't have the answer here. I think definitely it's possible to use Euler-Lagrange approach with inequality constraints as well. And in that case, I don't know if it's easier, if it's harder. I don't know. I think it's interesting to see, but all right, for equality constraints, I think it's necessary to...
Just a question. Let me jump in because I was kind of lost in the middle of your description about the constraint that has bothered you. Which one is it exactly? So you mentioned that...
It is the subject 2 in equation 5.39.
5.
Ax dot 2 dot equals to b.
5.39. Let me see here. Okay, so this constraint, you see a problem with it?
No, what I'm saying is that every time this constraint appears, when both in the thesis and also in many researches that I did in looking into articles and all, they come either from a holonomic constraint, differentiating it twice. Okay, if you have a holonomic constraint, differentiate, you obtain it. Or from a Pfaffian constraint, differentiating it once. The thing is, in both cases, holonomic constraint and Pfaffian constraint, you can use the Lagrange multipliers and obtain the solution very easily with the same computational complexity, essentially, I mean, asymptotically the same complexity as this approach over here. So I don't see why. Okay, there is some novelty, there is some merit in trying to discover new things, but I don't see why it justifies for equality constraints once they all come, at least all that I saw, from Pfaffian or holonomic constraints, which you can handle very easily with the same complexity asymptotically in Euler-Lagrange equations.
Okay, so now I understand what you said. I'm going to address that remark when it's my time to speak. Thank you so much. Please go on, continue. Thank you, Vinicius.
Right. So this is it, Juan. I think maybe you should emphasize that for inequality constraints, definitely there's something to look for, but for equality constraints, I don't know, at least for me, all the examples that I saw, it's always the case that it comes from a holonomic or Pfaffian constraint, so it's the same in terms of complexity, right? All right, okay. So moving on. Okay, I have just another question about experiments. Did you have problems with shattering in the control action? Because when you use these approaches based in optimization, sometimes you have a lot of problems with shattering in the control input, right? The control input oscillates a lot. And in your experiments, when I see the graphics, I don't see this problem at all. But maybe you choose the good experiments and the ones with a lot of shattering you remove. I don't know. Did you have this problem?
You mean, excuse me, can you repeat the question? Shattering about what? I missed the question.
The control inputs. When you use the control input from an optimization problem, as you do, you compute the control input using an optimization problem, right?
Right.
Normally, at least in my experience, there's a lot of shattering in the control input. There's a lot of oscillations, very high frequency oscillations. And it's not the case in your experiments here. So I was wondering if you had this problem and removed those experiments which had this problem, or every time you tried, it was as smooth as it is here?
No, actually, every time I tried experiments, I obtained the results. In fact, the vector field inequality generates control inputs less smoother, as for instance in figure 6.3, you can see that the control inputs, the norm of the control inputs are different, are higher. The control effort is higher in the case of in the constrained case, but actually that the results which are presented are the results that I obtained every time I run the experiments. I remember that one time I obtained a shattering, but the problem in this specific case was a error in the computation of the Jacobian, an implementation error, a typo. But actually, the results that are presented are the same that I obtain every time I run the experiment, in which were a lot of experiments in order to get a cool simulation and implementation.
Okay. Right. Okay, that's interesting, because sometimes there is this problem you didn't have, maybe because you use quadratic problems. Sometimes I use linear programs and they are more prone to this kind of behavior.
Yes.
But all right, that's yes, you use the linear programs in your master.
Yes. In that case, I observed shattering of between the control inputs. It's true in that case.
Okay, fine. So that's all. I made some comments here, but overall, I will repeat that I like a lot your document. I like a lot your presentation and your work overall. I definitely think it's worth a doctoral degree. And I want to congratulate you and congratulate Bruno. And this is it.
Thank you so much.
Thank you so much for your considerations, Vinicius. Now I hand over to Luciano. So please, Luciano, do your considerations.
Okay, so thank you, Bruno. Thank you, Juan, for the invitation. I agree with Vinicius. So I believe that this is a solid PhD work. I have any doubt about that. So I like the text written. I also like your presentation. So I don't have any doubt about the fact that if this is a PhD or not. So it is indeed a PhD work. So don't have to worry about that. Very nice work. Okay, I have a few questions here. Basically, I would say that they are more like curiosity, I would say. Find them here. Okay, so my first question, chapter 3. I'm not a specialist in task space control. Curiosity here. So basically, you mentioned that the derivative of your desired task is equal to 0. Is there anything that prevents you to consider time varying tasks?
No, in fact, you can use tasks that are not constants, of course. In that case, there is no guarantee of the robot is to reach the desired pose or position or orientation. But in those cases, you can use an additional terms. It's called the feed-forward term, in order to minimize the error and to reach the desired trajectory, for instance. But of course, it is not limited to constant decided tasks. Can be variables.
Okay, but then you would have a different maybe objective function.
Yes, in fact, you can perform can write the optimization problems in a multi-objective way. But in that case, you have different objectives, and the fulfillment of one task in an objective can have an influence of the other objectives. So in that case, you can assign a weighted optimization to try to separate the error dynamics of the different tasks, but still you can, the fulfillment of one text can have an influence of others. Of course, you can also use hierarchical quadratic programs where you can separate the different priorities and you can solve first an optimization problem. Like for instance, in equation 3.5 to 3.6, it's a way to perform, to separate, to take into account different tasks with different priorities. But of course, you can use different or several objectives in the main objective function in the equation 3.1.
Okay. Equation 3.2 have this minimization here. You mentioned that this is an unconstrained case, but actually you have constraints.
Ah, it's true.
Okay.
It's a type.
Just the type. Okay. I think in this equation 3.4, you have this G function, right?
Right.
So this G function is a function of the norm of the vector.
Well,
I'm saying this just because you define G as mapping from real to an interval, right? So then you should have real here, real number.
But in that case, G is defined as the norm of the time derivative of the tax error, right?
Okay, then you should have the norm here.
Yes, we want here, actually it's a real number, that function, which is multiplied by a vector of a suitable dimension vector in order to take into account the constraints, for instance, the velocity, the joint velocities is a vector. So we need the same vector. We need a vector. Because of that, we multiplied the vector of n-dimensional vector times the real number, which is composed by the G function that depends on the tax error.
Yeah, okay, but I'm just mentioning that maybe in 3.4 you should already have the norm of x dot here instead of having x dot, right?
X dot, yes.
No, but should have the norm.
Yes, the norm. We require the norm.
Just to agree with the definition regarding G.
Let me jump in. So yes, the domain is incorrect, Luciano, here.
Okay. Okay. All right.
Yes,
all right.
because it should be Rn.
Okay. Okay. Then yeah, that's the
It's just but it's just a typo. Yeah, but it should be Rn.
Missed the question.
So, okay. Then you have this equation 3.7. Basically, what you're doing here is a kind of back linearization, right? Approach. So basically, you want to compute the torque inputs, right?
Yes, in those cases.
So then, yeah, my curiosity here is that about the robustness of this approach. So it's just like curiosity. Maybe you did some experiments or maybe some simulations. So what happens if you have some uncertainty in your parameters?
Yes, in fact, it's a limitation of this approach because we assume that we know perfectly the inertial parameters of the robot, which in real application that maybe it's not right, it's not correct, or it's not possible. In our simulation, the robot works without problem because we know the perfect inertial parameters used on the rep, And still, maybe for small uncertainties, the system is in a closed loop control. So in that case, the robot works perfectly, but of course with using a different parameters from the simulator, which I changed to illustrate or to observe the behavior.
So you have run this kind of simulation. So you have
Exactly.
observed the okay. And it
Using
works only for very small
yes, for very small
change
difference.
if you increase this perturbation, then you have problems.
Exactly.
And maybe one thing that could be interesting is maybe to investigate something related to robust optimization.
Yes.
So this is not a specialist on that, but I've already seen some works. Basically, the guys in this field is an area inside the optimization area which deals with this problem when you have uncertain parameters in your formulation. Maybe by using this kind of algorithms.
Yes, indeed.
So I have another question, which is actually it's similar to this one. So chapter 4, have page 21. You mention here that it's assumed that the residual is null. So have you considered examples in which maybe you have some perturbation, this knowledge of the residual?
No,
But
in
this
this
might
case,
be actually maybe this is related to the velocity of an object, for example, right?
yes, velocity and acceleration even.
Okay.
Of course, here we assume that we know the velocity and acceleration of the object perfectly. And also this can work, for instance, for two robots sharing the workspaces where you have a unified control lot to control both controllers. In that case, you can obtain easily the information about the velocity and acceleration of the object. In this case, the residual contains the velocity of the other robot sharing the workspaces. But of course, in case of a dynamic object, we need additional strategies to estimate the velocity and acceleration. But of course, that here is assumed that the information is available and is perfectly known.
Have you run any kind of simulation just to see the behavior?
Yes, of course. At the moment that you miss the information about the object, the robot collide. Well, at least there is no guarantee of prevent collision. In fact, that what's illustrated.
Yeah, but then you had the extreme case.
Yes,
right?
an extreme
you
case.
don't know, but maybe you know, but not exactly. Have some uncertainty knowledge.
But that simulation I don't was not performed, but I probably you have problems to estimate that residual, the proof that shows that the prevents collisions doesn't work anymore, because I assume that you know perfectly the residual.
Okay.
So there is no guarantee of prevent collision.
So actually, you need here in your approach, you need the velocity and acceleration of the obstacle, right?
Yes, in this case, it's second order dynamics. So you have acceleration, you take into account as well.
So yeah, now I have questions, actually, curiosity. So in this chapter 4, first you consider the second order kinematics, right? Then you extended the VFI framework, consider second order kinematics. And then in other part of the chapter, you consider the support polygon area. You also consider multi-contact applications, right?
Right.
So, but then in this case, you consider only joint velocities.
Yes, it's true.
So is there anything special about the extending this to second order, or there any kind of issue?
In fact, it's a future words. The idea is to use the second order vector fields inequality in multi-contact application in order to enable richer models, for instance, the dynamic model, to take into account the force and moments acting on the body. But of course, it was only explored in first order kinematics because the pandemic situation was complicated to perform experiments, and because our robot is commanded by joint velocities only. So future works will focus it in that implementation, first in simulation, of course, in future works as well in real platforms of robots, human robots commanded by joint torques.
Now, regarding your algorithm, use the dynamic model. I have here this complex table 5.4. So, do you have any idea maybe how to increase this cost? Maybe using, I don't know, maybe improving the algorithm somehow. Have you started thinking about that?
Well, at the moment, I don't think about it because at the first moment we are interested in theoretical aspects, but maybe the idea is to find a way to describe the algorithms using recursive strategies in order to obtain a better performance. But in those cases, when you want a better performance and still use dual quaternions, I think it's a better option use the Newton-Euler algorithm, which is available again as well in dual quaternion algebra.
Luciano, can I make a question? You remind me of something.
Yeah.
Okay. One, if you want to model using your approach, robotic manipulator, the only constraint you will have to consider using the I always forgot the name. Just a second. The Calabi-Udvari approach, if you want to model a robotic manipulator without any other constraints other than the unitary norm constraint you consider in section 5.4.3, I mean, if you want to model just a robotic manipulator, the only constraint you need to consider is constraint 5.54. Suppose you want to model.
Excuse me, what constraints?
5.54. 54. Suppose you want to model a robotic manipulator. the only constraint you need to consider into the acceleration in the Cadavala approach, I always forget the name, is the one in 5.54? Or there are other constraints you need to consider when modeling a robotic manipulator, for example?
Well, in case of a robot manipulator, there is not additional constraints. The term, the matrix A and the vector B, is not required to describe the robot's modeling. In this case, in this specific case, the equation leads to the case of the constraint case. The solution is the same, given by the Gauss principle of least constraints without any additional constraint.
So, I mean, why do you, when you differentiate, when you derive, the better word, the second order constraint for this holonomic constraint in equation 5.58, do you use this constraint somewhere else, or is just an example? In equation 5.58, you obtain an acceleration constraint, right? Do you use this constraint somewhere else in this document, or is just an example?
It's just an example. The future words idea is to, in fact, a question to Professor Luciano, is to use the second order vector field inequality in application of the support polygon of the multi-contacts. In those cases, we use, the idea is to use a dynamic model of the robot manipulator. In that specific case, we use this equation, but at this moment, what's an example? And that equation, that modeling, it wasn't used in this PhD dissertation.
Wait a minute.
Okay.
Just a second. Let me jump in. So you simulated a mobile manipulator with a holonomic base, right? Also.
Yes.
So you had to use this constraint.
But exactly that constraints, because that's a constraint related to the unit norm of the unit dual quaternion.
Okay, but if you use a mobile base, don't
yes,
you need...
in case of non-holonomic constraints, that model was used.
I'm saying a holonomic base, holonomic, without any non-holonomic constraint. But you need still the information about the pose of the mobile base with respect to a reference coordinate system, which is described by a dual quaternion with unit norm. So you need that information.
Yes, that's my point.
But in those cases, the mobile platform was represented by the vector x, y, and phi.
Well, if you want to, but I mean, a mobile base can be terrestrial or can be aerial. If it's aerial,
yes, of course. In case.
So that was the question that Professor Vinicius made.
Okay, now in those cases, when in this dissertation, the model platform of the holonomic base of the robot was represented using a vector and wasn't represented using a unit dual quaternion. But if you want to use a unit dual quaternion, in those cases, of course, that constraints arise. You can use that equation.
Because it's kind of weird because you advertise dual quaternions and then you don't use it. I mean,
yes, but it's in the case of the humanoid robot, or in case of you aerial robot, you use a unit dual quaternion. But the idea is only to illustrate an example of how to model a humanoid robot.
Okay. Nevertheless, all right. It's fine. I understood. Sorry, Luciano. Sorry.
No, don't worry. Okay. Okay. Well, now I'm here in page 75. Also another curiosity. Basically, you mentioned here that you have small violations of the joint limits, right? And then you say that this is due to discretization effects, and also because of the movement of the non-holonomic robot. So, are these the only things that you think that would cause this problem, or did you think about other things too?
I think that the main problems are there. For instance, that effect can be seen in a simulation when you
Okay,
on
so you
VREP.
have that in simulations too.
Yes, you change the discretization step, the phenomena appears, and you can observe. In case where the robot have the movement of the non-logarithmic wide platform that was observed only in the real experiment, because the robot has the small movement of his torso, because the movement of the base that it's not taken into account the kinematic model.
So then you mentioned in page 90, you mentioned about this issue related to abrupt through inputs, right? So have you thought about considering this issue in your optimization formulation? Trying to address this problem. I'm asking this because some people do that in MPC. They try to have smoother inputs, but they change their formulation.
Yes, no, at the moment there was only a phenomenon observed. This is expected as well, the higher control effort. But of course, that problem was not addressed.
Then okay, in the end of your conclusion, you also mentioned about this. What this is something interesting. So you mentioned about these theoretical questions about how to perform an optimization over the ring of dual quaternions. So, have you seen any work trying to do that? Is there anything out there? Or
And not to my best knowledge, I don't see that formulation. I think it's a challenge topic, but it's a very challenge. I don't know who's working on it, on the formulation of the hypercomplex form of dual quaternions.
okay, very nice. Okay, Juan, I'm done. So congratulations for work. Thanks again for the invitation. And so maybe just a personal question. What are you going to do next?
But I accepted a proposal to a PhD to a work in the Arada laboratory in the Tokyo University in a postdoc fellow. So I am working on it.
Cool. Very nice.
Thank you.
Great. Very nice. Congratulations.
Thank you so much for your considerations, Luciano. So I'm going to try to summarize everything here. But first, I would like to thank you all for being part of this PhD committee. All of you made several important remarks that we're going to take into consideration, of course. And I really appreciate your time. So now we're working with four time zones. So we're working with the Brazilian one, the English one, the French one, which is just 1 hour difference from me here, and the Japanese one. So yes, I really appreciate your time and your willingness in participate in this PhD committee. I would like to address specifically some comments and remarks, especially those more philosophical ones, because actually a PhD thesis is always inserted into a broader context. So some choices that a PhD candidate presents is not always coming from that particular work, but also from a broader picture, I would say like that. So one thing is related to dual quaternion algebra, because of course, although this is a mathematical tool that is not exactly new, because it was proposed by Clifford in the 19th century, few decades later after Hamilton proposed the quaternions. But yeah, during the vector wars that happened when Gibbs and other mathematicians appeared in the mathematical scene, so it appeared that vectors, for some reason, gained more traction and have been used up to the 80s of the last century, so 1980s. And then physicists and other researchers realized that as a mathematical tool, vector algebra in general offers, actually is quite limited. So it cannot, it doesn't allow you to express logical relationships and geometrical relationships as effectively as the more general Clifford algebras. And dual quaternion has a strong relation to Clifford algebras, but it's not exactly a Clifford, it's isomorphic to one type of Clifford algebra, but it's not exactly the Clifford algebra. Is equivalent up to isomorphism, of course. And one of the reasons why we use in our group dual quaternion algebra can be motivated by Featherstone himself. So these will address some of the comments that Abderrahman made. So I'm going to quote one paragraph of one of Featherstone's papers, more specifically, A Beginner's Guide to 6D Vectors, Part 1, that Featherstone published in IEEE Robotics and Automation magazine in 2010. Featherstone says, spatial vectors are closely related to screw theory, to motor algebra, and the Lie algebra SE3. Screw theory emphasizes geometrical aspects of 6D vectors, which are the vectors that Featherstone uses. So expressed in terms of straight lines, pitches of screws, and magnitudes. Lie algebra takes a more formal approach. SE3 is the tangent space at the identity of the Lie group SE3, the lowercase SE3, of course. So you can expect notions of group theory, manifolds, and tangent spaces to appear. Motor algebra has two forms, one based on real numbers and the other on dual numbers. The latter is not suitable for dynamics because dual numbers don't work with inertias. So now this is the point that I would like to highlight, because first, dual quaternion algebra, in its specific, in its particular form of unit dual quaternions, this is a Lie group because it is a group, and both forward and inverse maps are differentiable. So it is a Lie group. So we have the formalism of Lie theory to use with dual quaternion algebra, but also it represents in terms of geometry a screw. So it connects, unit dual quaternions connect screw theory with Lie algebra. So they do something that the algebra of 6D vectors of Featherstone doesn't do. So actually there is this theoretical connection, but more than that, and this is the irony here, because what Featherstone says here is that motor algebra, when using dual numbers, cannot be used to represent dynamics because it doesn't work with inertias. And we proved him wrong, because actually in our paper that we submitted and is currently under evaluation, in which Juan José is one of the co-authors, we proved that yes, we can represent inertias by means of dyadics or something similar to dyadics directly in the formulation of dual quaternion algebra, which unifies motor algebra, screw theory, and Lie algebra. So this, from a theoretical point of view, offers a lot of insights and, mathematical reasoning. And there is something that Featherstone himself says in his paper, which I think, which is very important. Actually, he said it to defend his work, but it also applied to our formalism. He says, however, anyone who thinks that 6D vectors are only a convenient notation for organizing 3D vectors is missing half the point. 6D vectors are tools for thought. They have their own physical meanings and mathematical properties. They let you solve a problem more directly and at a higher level of abstraction by letting you think in 6D, which is easier than it sounds. So what we've been doing for more than a decade now is offering mathematical tools that unifies different fields of mechanisms, robotics, and mathematics in general, and doing something that Featherstone himself thought it wasn't possible. For example, designing dynamic representations using dual quaternion algebra. We did it. And there is one important point, which for us roboticists, I would say it's extremely important, is the usability. So of course, computational complexity is very important. So in our formulation, we weren't concerned at all with computational efficiency at that point. And why? Because the algorithms are already efficient enough. So they work in real time for, 50 degrees of freedom robots. We can do it already with that formulation. But there is one important thing. Thanks to the abstractions that we use, and this is thanks to the algebra, right? If we change the computational complexity from the basic operations underlying the implementation, all the other algorithms will benefit from that simplification in terms of, or that improvement in terms of computational efficiency. And in our formulation, for example, when we derive those formulations, we need to use a lot of dot products, cross products between plucker lines, and the current implementation is not efficient at all. And why? Because we weren't concerned. So just if we change some lower level implementations of our libraries, we can reduce by 1 or 2 order of magnitudes. So we can, I mean, if we have a polynomial, a third degree of third degree, we can reduce easily to a polynomial of second degree. And we can come up to Featherstone library. This is a conjecture because we haven't done it yet, but yes, we can be very competitive with this state of the art. But our main point here was to, in terms of our whole research group, is to work on that theoretical aspects. So sometimes, as you all know, we have to give 2 steps back in order to advance 30 meters forward. And this is what we've been doing. So when I did my PhD, the question was why I'm using dual quaternions to represent kinematics. And then I was able to implement a lot of things and represent a lot of things in a very compact way, just doing model composition very easily. So it was done. And then everybody accepted it. And then we continued with other kind of developments. And now, little by little, people are starting to get more convinced. But of course, there are always some theoretical gaps and other gaps. And I thank you all for remarking, for example, this kind of issues with computational complexity. But at this moment, we weren't concerned with those aspects. But we were concerned with addressing the points that I read to you all, points that Featherstone himself mentioned. And that, honestly, I would say people usually don't like when I say this, but Featherstone took a very utilitarian approach. So if you see what he did is amazing, it's very efficient, but if you want to do, if you want to gather insights, which are usually very important when you want to prove some properties, it's very difficult using directly that representation, because that is meant to be efficiently in terms of implementation, but it offers several abstractions, but in my opinion, they are not good enough. So what we've been doing, I think it's more powerful, but let's see. Regarding other kind of things, so I of course, it's the question that you posed up there was really to the point regarding the kind of geometrical primitives. So what we do is really simple for the moment. Again, we weren't concerned with meshes, and we've been receiving those kind of remarks over and over. So another person that made exactly the same point was Russell Taylor, the professor from Johns Hopkins working on medical robotics, because for him, it's very important to consider a mesh, and then especially if you are doing surgery. So yes, this is really important. We have some insights. Our approach is starting to deviate from meshes, but take into account more refined things. So one inspiration that we currently have is from people also from Johns Hopkins. So Greg Chirigan, so he works especially using representation in Minkowski spaces, in which he can represent more complicated shapes. But the thing is, all those shapes, they are differentiable, which means that they are smooth. For example, it's possible to have something that is very close to a cube, just to exemplify what I want to say, but the corners are rounded. So if you do like that, it's not conservative anymore, because the precision is up to you to choose what best suits you. But the thing is, it's differentiable, and then for control, it has very nice properties. So that is the path I want to follow in terms of that part. We haven't done anything substantial on that yet, but that's the future. But I really appreciate the importance of having something more refined, and I do agree that what we've done so far, at least in terms of the geometrical primitives, was simple. But then again, depending on how we do it, I still think that we can benefit from the geometrical properties offered by dual quaternion algebra to help in transforming those things in a very efficient way. For example, even if you have a mesh and you want to transform it, I think that we can do it computationally efficient, in a computationally efficient way by using proper transformations. But again, this is this to me at this point is a little bit more secondary. That's why we haven't dealt with it too much. And yes, I'm looking forward for your comments about the multi-contact thing, because again, although we are just starting doing that, you have, I don't know, dozens, several dozens of works just on that topic. And I'm really looking forward to see your remarks, because this is something that we're starting strongly to work on now. So here at the University of Manchester, I have now 3 students working on that. And really, so here now we have a hexapod, and the goal is to do chimney walking, in which, for example, the hexapod must climb up a chimney, choosing the footholds and adequately, and this imposes multi-contact problems. And yes, I'm really looking forward to your remarks on that. Yes, so I hope from the dual quaternion algebra, I hope it's more motivated now, because again, of course, it wasn't Juan José's responsibility to show this broader picture, because this comes from a much larger group. But yes, that's the main reason. I would like, before going to the next step of our PhD committee, I just wanted to address some questions that Vinicius mentioned as well about feasibility. Yes, Vinicius, this problem is really hard. So Abderrahman has several students working on the problem of feasibility. We had a similar discussion. I participated in a committee for his PhD students last week, and we had a similar discussion. And of course, for the extremely general case, it's really difficult to show feasibility. And also, one important thing that Abderrahman mentioned in our last conversation that I take the liberty of replicating here because it's really up to the point, is that actually the problem is still more difficult because usually you don't know beforehand what the constraints are, because you cannot take all of them into account at the same time, because sometimes you have thousands, even millions of constraints. And what you can do is only to take into account local constraints when you are in a particular area doing a particular task. So you have to put and remove constraints all the time, which, you know, inserts discontinuities and makes the problem much harder. So even if you have all the constraints together, you are able to do that. It's already harder. It's already hard, but it can be still harder. So one problem that Abderrahman mentioned was about the problem that you are dealing, right, Abderrahman, with Airbus, in which you have a humanoid within aircraft manufacturing site doing a lot of different stuff with thousands, maybe millions of constraints that can be possibly happen, right? So it's a lot. I mean, it's very complicated. But what we can do is to define the constraints in a clever way. And if we assume, for example, if obstacles are static, the problem is much easier, because now we don't have problems. You know, if we use the dilemma that we've proposed in Juancho's work, so we ensure that we can always maintain a distance greater than 0 for each obstacle, and we can do this all the time, because actually we can, if the obstacles are static, so then the problem is easier. But of course, if obstacles start to move, then it starts to become more complicated, of course, and then it's very difficult to guarantee unless you assume some inner characteristics of your robot, or if you assume also actually not or, and you assume also some kind of movements that the objects are allowed to do, of course. Yeah, so one point that Abderrahman mentioned that I forgot to say, but actually the residual term that we have there, actually sometimes it is not important but essential to have them, because even if you use the local coordinate system, the robot's coordinate system, that term still appears, because actually if you think about what's happening here, we have a function of the configuration and of time. So that term, the residual, is just the derivative, the partial derivative of the function with respect to time. It appears either in the robot frame or in the global frame. It doesn't matter, because it's related to the motion of the obstacle with respect to the robot, but without influence of the robot. So for example, if you disregard it, we have some experiments that we did for transactional robotics in 2019. So there is a situation, for example, if you can only measure the obstacle's position, but not the velocity, it may be the case, especially due to the discretization, that at a given instant, your constraint is violated, because you don't have the information about the robot, about the obstacle velocity. You have just the instantaneous information about where the object is. So that information is really, it comes from the partial derivative with respect to time. It's a term that exists regardless of the frame. So it's important to highlight that. And maybe Juan, maybe this is something that you should highlight in the PhD dissertation, because this was a comment that Luciano made during your qualifying exam. And this can generate a lot of confusion, and it's better to just highlight it. And there are two things that actually, some things that Vinicius mentioned, and they are really important. And one thing is very important related to chattering. So Vinicius, for all my students, one thing that you can rest assured, you can be really, really sure that they will never remove data points from the results just to make them prettier, because this is first unethical, right? So yeah.
Bruno, just a thing. Sorry, I didn't say remove data points. I mean removing maybe an experiment.
No,
the entire experiment.
No, this is equivalent of removing a data point in the set of experiments, not the data point of a experiment, a particular experiment. But if you have a bunch of experiments and then you cherry pick them to highlight just the best ones, so this is unethical. This is not science must be done, should be done. So yes, what you see is what you get. That's the main point. And we as examiners and as advisors, we cannot accept those kind of things. And yes, so I always check the raw data as well. But one reason that it's harder to see the chattering. It's one of the reasons is what you mentioned. What we use is first quadratic program, and we have the damping term, which makes the solution unique. Therefore, what happens is that we have some kind of continuity. The discontinuity may happen when one of the constraints is activated. So of course, there are those kind of discontinuities, but overall, the problem is well behaved. And in addition to that, it is widely well known that a robot system acts as a mechanical filter. It's a second order mechanical filter. So it's filtering the signal as well. So if you have a controller that is well behaved, like a quadratic program with the damping term, which makes the solution unique. And also on top of that, you have mechanical filters, which are robots. So of course, you won't see any kind of major chattering. You see, of course, but not as frequently as you would expect if you are doing just simulations using linear programs with a kinematic model, which, yeah, what we're doing is not MATLAB. What we're doing is implementing on real robots. And one point that it's kind of, I would say, kind of ironic, because we discussed that on Monday when Juan was doing his presentation for the whole group about expressions 4.53 up to 4.56. So that point that you, Vinicius, mentioned about J times Q dot equals 0. So we discussed that, and I think that Juan forgot to say that one of the reasons, if you want to, may you please open the thesis on equation 4.53, please? Yes, 4.53, and share with us. Yes, that's it. So yes, Vinicius, you are completely right. If you want to fix the end effector, or end effector position, end effector orientation, or something like that, of course you should do something that has a proportional term. But the thing is, as Juan explained quite well, the physical phenomenon underlying what's happening here prevents the robot from moving. But more than that, there is a mathematical reasoning for doing so as well. First, we take leverage of the physical phenomenon. So this is the first thing. The second is that constraints 4.53 up to 4.56, because they allow mathematically a small drift, they are easily more mutually compatible compared to the situation if you had, if you fixed, all the points at the same time, because now you have a tougher problem to solve. You really say, I want the end effector to stay at that particular pose no matter what. And then if for some reason it's impossible for the robot to do that, of course, the control law will become unfeasible. Whereas in this case, what will happen invariably, because it's very easy for the robots to project the control signal into the null spaces of those matrices, what you'll see is a small drift that will be prevented by the physical interaction. So there's a mathematical reasoning behind it as well. And yes, and one thing that I would like to mention about the Uduadia-Calaba equations, that I think it's not fair what you said, in the sense that, well, if you're exchanging potatoes for potatoes, so if you like, Euler-Lagrange derived by using Lagrange multipliers, and you know that it's equivalent to another technique, so you can use another technique, and it's equally, if it's computationally equivalent, if it's mathematically equivalent, so you cannot say that one is better than the other. So it's just up to you and your preference. So it's not fair to say that I don't see any advantage. Therefore, you should have used, or I would recommend using the other approach, because they are both equivalent. But on top of that, what I would say is that in terms of presenting the results, because we all know all of them, so we can use whatever we want. It's not a technical challenge. It's not a main source of difficulty. But there is one thing that I can say, though. One of the beauty of the Uduadia-Calaba formulation, which was proposed in the 80s, is that you can solve a quadratic optimization problem with constraints without knowing anything about optimization at all, actually. What you just need to do is to know matrix algebra and linear algebra in general. That's it. So it's a very simple formulation. Of course, one can argue that Lagrange multipliers are very simple as well. Yes, I agree. They are both simple. And I would like to quote one of my colleagues, Professor Ishihara. Well, when you prove a theorem, it becomes immediately a trivial thing because it's already proven, right? So if both formulations have been proven to represent the same thing, yes, they are both trivial in essence. So that's the main point. But what I like about
Bruno.
Yes, please.
So I might give you a few things, because these problems actually will appear. So I will give you an anecdotic story. Okay, I was with a mathematician lady, pure mathematicians, on a summer school on non-smooth mechanics, and she made a whole story about a point hitting a wall. Okay, like this is a constraints basically, and I was amazed how much of theory you can build, okay, out of a point in terms of pure fundamental mathematics. But I told her, well, I said, this problem we have solved already by using numerics. And she confessed, she said, yeah, I will tell you something. People who do numerics, who do algorithmics, are advanced about 20 years on people who are doing fundamental aspects. So choosing a formulation with respect to the other, it depends really what you want to do with it. Like a Newton-Euler formulation is good for fast computation. Okay, but if you want to use it to prove control stability, it's not possible. Then you better use the Lagrange approach because it's a closed form. So if you want to compute fast, you can use something, okay, much of a numeric, but you cannot use to do anything with it in control. Or you can use a formulation, okay, which is closed form, then it's not extremely fast to compute, but still it is closed form. So to do control, it's better to use this. That's why people who do control prefer to use closed forms, expressions of the dynamics, like or Lagrange, etc. Then people who are doing numerics who prefer probably other things, okay, because they compute fast. And I think that Vinicius has also a point with respect to these constraints that you were mentioning. You will really see the problem with these constraints when you will integrate forces and when you want to do really contact with the robot and you have uncertainties. Because then clearly the PP will become feasible. We witnessed it several times, okay, when we do real experiment on the robot and these contacts through establishing holonomic constraints doesn't work in practice. Okay, they are very good in simulation. You can do out of good experiment with them, but clearly we had to use, for instance, instead of 0, adding a small noise theta that is just to make the QP feasible. But like this, if you do the simulation like ASA, we didn't see them. And it has to go through real experiment where you have a little bit of these uncertainties, where these problems will pop up really. And then you will see, now we are not using this, for instance, to do contact. We are using full admittance control as constraints and as task to do this instead of using these differential Jacobians multiplied by the velocity. So in theory, in a perfect world, they work perfectly well. In practice, well, they are not really robust and they are extremely sensitive to noise. So that's probably what Vinicius wanted to say. It's that, I mean, if you have a little bit of noise, that might be a problematic.
But it's not the point I was addressing in his remarks. Everything you said, I completely agree. The robustness of those algorithms, etc. I was actually arguing against the comparison between the derivation of the final solution by using Lagrange multipliers versus using Udwadi-Kalaba equations, because actually what you mentioned will affect both techniques, because both are addressing equality constraints and arriving at the very same equations. So what you said is one step further, I would say. So what you're saying is that, well, both equations, both methodologies will have the same problems because they are equivalent. That's the point. What I was addressing instead.
No, in your case, I mean, the justification is very easy because you are preparing a lot of things based on dual algebra, dual quaternion, sorry, and you want everything to be coherent. I mean, for me, it's not shocking that you are trying to do the dynamics with dual quaternions because it's the tool that you are doing. I mean, it doesn't make sense also to use constraints with it's not forbidden, of course, but I assume that you would like to prepare a framework which is fully coherent in terms of the tools that you are using to model your problem. And it might be that if you use the dynamics, which is not really using dual quaternion, and you use the other thing by using another algebra, probably, I don't know how it would behave. I don't know how, maybe your problem will be just too much, okay? You will use many decision variables that you have to also put constraints between them to link. This reminds me where we're doing optimization of manifolds. So it was better to write everything in the manifold, in the same manifold that we're using, instead of trying to do an equation in this space and another thing in another space. So I think it could simply be justified by the fact that you are using a specific algebra and the specific tools, and you would like all your dynamic equations and kinematics be coherent inside your controller and the way you formulate your QP control.
Precisely, yes. It's exactly that motivation. Yes, precisely. So what I addressed here was just of a more philosophical nature, because there, as you know, we always have this kind of discussions, philosophical discussions of which technique is best. I remember François Chomet hammering me in one of the Journée Nationale de la Robotique Humanoide, because he wasn't convinced why dual quaternions were better than quaternions plus 3D vectors. And at the time, I was a PhD student. I was in my first year. So I was just looking the problem through the prism of rigid motions. And yes, if you consider just rigid motions, there is not too many advantages. But then after you mature and you get a more mature idea, you see that, yes, there are some algebraic advantages. And as you mentioned, the idea is then to have a coherent framework. Yes, precisely. But yes, that's it. I just wanted to talk about those points because they are prevalent in what we see, and it's very important to make everything clear on that respect in terms of our strategies for doing research. So now what I'm going to do, so we have to go to another room, all the members of the jury except Juan José. And I would like, so now I'm going to speak in Portuguese because I need to talk to the technicians here. And that's it, just a second. So, Luciano, do audiovisual, por favor. Você poderia, então, interromper agora a transmissão ao vivo para o YouTube, enquanto a gente vai para uma outra sala. Se você puder abrir um breaking out room here, breaking room, não sei como é que chama, para que os... Tá, joia, obrigado. Obrigado. So we're back after deliberation among all the members in the PhD committee. We have decided that you, Juan José Quiroz Omaña, has been awarded the degree of PhD. Congratulations. And more than that, something that in my considerations I omitted, and now I'm going to say it. So thank you so much for being my students all those years. We've known each other for now 6 years and a half, I guess.
Yes.
So yeah, so you did the MSc with me, and then you continued during the PhD, and it's always been a very good student, an outstanding person, really a good addition to our research group. And I'm really grateful that you stay with us this whole time, contributing not only with your PhD studies, that it's visible that you did a very nice job, but also contributing to the laboratory, helping in organizing things there. And that is really much appreciated. I really much appreciate it. And yes, I wish you all the best in the continuation of your academic life. And I really do believe that you're going to have a very good time in Murilo's group. And that's it. So
thank you so much, Professor Bruno. Thank you so much. Thank you so much.
Okay.
Congratulations, Juan.
Congratulations, Juan.
Thank you.
Congratulations.
Thank you.
So yes, thank you all again. Now,
Congratulations.
Thank you, Professor Keder.
Now this session is officially over. Thank you again for everything. Bye.
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 Thank you so much.
Bye bye.
See you.